Hi, I'm Lawrence.
Hello, my name is Pranav.
Hi, I'm Richard Key.
Hi, my name is Aniket, and this is our Coyote Creek Hill Health Station.
With this project, our goals are to monitor the overall health of the Coyote Creek ecosystem, to explore the field of earth science through measuring various aspects of it, and to familiarize ourselves with and expand our knowledge of programmable microcontrollers.
Okay, so first, a little background on Coyote Creek. Contrary to the name, Coyote Creek is actually less of a creek and more of a river since it runs 63 miles long and acts as a watershed which replenishes water all across Santa Clara. One of the main reasons we should be trying to protect Coyote Creek is because it's home to the most diverse ecological system of all Santa Clara watersheds. A good example of this is the endangered steelhead fish, which has historically used this river as a migration route. However, the population faced somewhat of a local extinction in the last 5 years due to land development in the area. So yeah, there has not been a successful migration of this fish in the last 5 years. And it's also important to monitor the creek health due to the ongoing pollution from industrial development and day-to-day littering, because amounts of pesticides, mercuries, and other toxic chemicals can be found in this river. And this is pretty significant since most of California's drinking water is supplied by watersheds in general.
Noise pollution is a prevalent problem in urban environments, and Highway 101, which is near Coyote Creek, is no exception. Excessive noise can be dangerous to humans by increasing the risk of heart disease and other cardiovascular problems. In animals, loud noises can adversely affect predator prey relationships, mating habits, and navigation and hearing capabilities. Our sound sensor has been calibrated to detect loud sounds and will output a message to the serial monitor whenever the noise level of the surrounding environment crosses the threshold. As the sensor does not discriminate between different types of sounds, it can also detect natural occurrences that produce large outputs of sound, such as thunderclaps and trees falling down. This component is important because it alerts residents of the area to loud noises, which are usually a cause for alarm to at least some degree.
Created a demo where an LED lights up every time I clap.
Air quality is an important aspect of Coyote Creek, especially due to the eccentric wildlife that live there. Without proper air quality, the wildlife that live near the environment will possibly die due to less oxygen consumption. We were able to measure the air quality reading due to an air quality sensor. The air quality sensor measures for different types of gases, such as carbon monoxide, carbon dioxide, methane, and many more. The sensor will then give a reading through the serial monitor based on if the sensor is sensing fresh air, low pollution, high pollution, or extremely toxic gas. And in that case, there is a serious air quality problem.
Temperature is an especially important aspect of the health of Coyote Creek and its surrounding areas, such as Highway 101. Due to being in a wildfire-prone area, an increase in temperature past a certain threshold could lead to devastating effects to the people and wildlife living in the area. This is especially true in periods such as now, where the entire state of California is in a severe drought. Our temperature sensor is able to measure the temperature of the area surrounding the probe. The sensor will then send out its readings to the serial monitor, where it will be continuously monitored. When temperatures reach high levels, such as in the summer or during heat waves, an alert will be sent out to the people in the area to be careful of their surroundings and to report any potential fires. The water quality of Coyote Creek is vital to the health of the entire Highway 101 area. Water quality and habitat problems in lakes and streams can continue to flow downstream and impact the entire ecosystem. There are many ways to quantify the quality of a body of water, such as visually looking at its appearance or monitoring dissolved oxygen levels. Our method of measuring water quality is through use of a pH sensor. Our pH sensor is mounted in such a way that the measuring bulb is always immersed in the water of the stream and will constantly print out readings to the serial monitor. We expect the pH of the water to remain within a healthy range of 6.5 to 8.5. If the pH of the water of the stream falls outside of the range for an extended period of time, residents of the area will be alerted, and data analysis can be done to identify the cause of the unexpected change in pH.
Okay, so what we have here is the distance sensor, and what we use this for is we measure the water levels of the river. So basically, we point it downward, and we can set like a threshold, so like it'll detect if an object is this close or this close, depending on what we set it as. So we could, the first thing we could do is we could aim it down, and we could just have it detect once it rises due to like flooding, and eventually the seafloor would go out of range, and it would tell us that like, oh, the water level is high. Or we could have it set the opposite way, where it could go down and detect once we're too close to the seafloor, and we could say that there's drought. So the reason this is important is because if the water level goes too low, then obviously, one, we're probably low on drinking water, and two, it could cut off water routes used for like fish migration. And the reason that we want to know if water is going too high is because obviously that could be a sign of droughts, and like people's homes could be underwater at that point.
So for the design process, our aim was to keep it compact and easily transportable. We thought our first design was to create a Tupperware container to protect the electronic components and provide buoyancy, and put the Arduino components inside. We did a first test, as you can see on the screen right now. Unfortunately, we realized that the pH sensor was going too far underwater, and we needed to some way to stabilize it. So we added a foam on the bottom and a hole in the foam to hold the pH sensor. That way the pH sensor wouldn't get like too deep underwater, which could cause problems. We also had the Arduino wired to a laptop, and once it was wired to the laptop, we could use it to pull it back like a tether. And the cable was quite long, as you can also see here. So for deploying the Coyote Creek Health Station, we placed the station in the creek, and we observed and recorded all the results that we got through the serial monitor. We took hourly values for each sensor and calculated the averages for several hours. That was the plan. Unfortunately, we didn't get enough time, so we got a few data points, and we'll talk about the results in the next section. Also, the sound sensor could not report on specific decibel level data, so that was also omitted. But we did get data for the air quality, the pH, the temperature, and the distance to see if there was an object or not.
For our data and results, we got an average pH of a little under 8, and the US national average for natural water is between 6.5 and 8.5. And actually, the optimal pH for river water is about 7.4. Our average air quality was fresh, which means that we did not detect significantly high amounts of gases such as carbon dioxide or methane. And while we did detect a small amount of pollutants in the air, that at one point that was probably due to somebody vaping nearby while we were testing out the sensor. For noise detection, the only loud noises we detected were our claps while we were testing out the sensor. And for our changes in water level, the area of the creek that we were testing at was too shallow, so we were not able to get an accurate reading for that sensor. And here on the right, you can see that I've entered our data into a Jupyter notebook in Google Colab. So for the in X, I've stored a tuple of tuples. We have the first value is the pH level. The second value is the sensor reading from the air quality sensor. And then for the Y tuple, we have the temperature in Fahrenheit. So I converted the data into NumPy arrays, used the sklearn library to create a statistical analysis of the data and create a model. We scored it and found the R-squared, or coefficient of determination, to be pretty high, but the sample was small, so it might not be that accurate, this model. Then at the bottom, I've plotted the pH level against the air quality. And as you can see, as one increases, the other sort of decreases. But again, the sample is small, so it's hard to tell exactly what the relationship is here. So overall, Coyote Creek seems to be healthy according to our measurements and calculations. And while there were some problems along the way, such as with our power supply and our wiring, which resulted in some of our sensors not being able to work properly, we were eventually able to fix those problems and get all of our sensors working together. So we learned that Arduino microcontrollers and sensors that are compatible with them can be programmed to perform a wide variety of useful and interesting tasks. And we also learned that earth science is a broad discipline with a wide variety of topics that can be studied. But here we chose to focus on the health of a local ecosystem. In the future, we hope to discover more about the ever expanding intersection between earth science and robotics. And lastly, we'd like to give a special thanks to Professor Celso, NASA, UC San Diego, and the National Science Foundation for this wonderful opportunity.